Hello. So one more video before we start the next chapter. So we're done with chapter 6 on divisibility, where we learned a lot of properties of integers. In chapter 8, we're going to start to study rational numbers. But I wanted to squeeze in some historical tidbits between these two chapters on the importance of the integer combination problem that we've been discussing and similar type of problems. So let me show you what I mean by that. So these are examples of what's called Diophantine equations. So Diophantine equations are polynomial equations with integer coefficients and any number of variables. So an example of Diophantine equation that you've seen before is Pythagoras equation. So a squared plus b squared equals to c squared. So anytime any positive numbers solve this Diophantine equation, then you could draw it as a right triangle. In general, though, it's a little bit more interesting to only restrict ourselves to integer solutions to these Diophantine equations. So integer coefficients and also the solutions are restricted to be integers. Turns out that it's very difficult to solve these things in general. One example of a set of equations like this is x cubed plus y cubed plus z cubed equals k. So what number k could be written as sum of 3 different cubes? They don't have to be different, just 3 cubes. It turns out that using some of the stuff that's a little bit out of scope for this class, but it's not too difficult, is that when this number k when is divided by 9, and if the remainder is either 4 or 5, you can show that this is impossible. The rest of the numbers is conjectured to be possible. In fact, it's conjectured that there should be infinitely many solutions that fit in there. But some of these numbers are actually super difficult to solve. One in particular that was just recently solved, that was a big deal. This was done last year, is 42. So x cubed plus y cubed plus z cubed equals to 42. 42, when you divide by 9, it's not a remainder 4 or 5. So people thought there were solutions, but no one could find it. It was just discovered that this combinations of numbers work. Of course, this is not a size of number where you can just brute force and try to plug in everything and see if it works. There were very clever optimization on what numbers to try and what numbers you can skip. But they did just with a lot of computing time on a supercomputer, and a very clever algorithm, they were able to find a set of solution. Another interesting one that was also solved last year, I think, was x cubed plus y cubed plus z cubed equals to 3. So this one is actually not difficult to solve. So 1, 1, 1 works. And if you look hard enough, you could also show that this is another solution. But for the longest time, for more than 60 years, I think, people couldn't find any other solution. And some people wondered if these two were the only solutions to this problem. But last year, they found another solution. I think the solution involved 21-digit numbers. So it's extremely rare to find these guys. And you might be thinking, okay, these are hard problems, but does it mean anything? The meaning could be added, which is the interesting part. So let me show you another Diophantine equation that's enormous, that has an interesting meaning. So non-negative range, so the non-negative output of the following polynomial. This isn't a random polynomial, so this is part of the polynomial. I had to go over to the next page. So this is where the polynomial ends. All the positive range for this polynomial is equal to the set of prime numbers. So, all the complexity of prime numbers was encoded into this one polynomial. It has 25 variables. I think all the letters from A through Z are used except for O, because O is a little bit confusing to write down. Yeah, so it talks about prime numbers. And I should put it in the context of what I've talked about in class already. So last historical tidbit video, I talked about Hilbert's 23 problems that was given in the year 1900. And this is Hilbert's 10th problem. This is one of the more interesting problems. So given a Diophantine equation with any number of variables with integer coefficients, devise a process, so find an algorithm, according to which it can be determined by a finite number of operations whether the equation is solvable in integers or not. Right? So this problem took about 70 years to solve after it was posed, but it was solved, and the solution was kind of in the disappointing direction. So here's a theorem. There does not exist an algorithm that will determine if an arbitrary Diophantine equation has integer solutions or not. So it was shown that it was impossible. But actually, I think like at this point, it should, at the time, it should have been expected, at least in the 70s, that this should have been impossible, because it turned out that a lot of like important key questions in mathematics could be encoded in terms of Diophantine equations. So this weird polynomial having positive range of prime numbers is not an accident. This was constructed using logic, right? Turns out that you could encode a lot of the unsolved problem in mathematics into a Diophantine equation and whether or not it has integer solution or not. You could do that with Riemann hypothesis. That's one of the $1 million problems. It's probably the most famous one, where it has something to do with distribution of prime numbers. But you could write down a polynomial that, if it has integer solutions, then it's equivalent to Riemann hypothesis being true. So a lot of, pretty much every logical statement, you can turn it into a Diophantine equation. So if there was an algorithm to solve whether or not the solution existed or not, he's not even asking for what the solution is. He's asking for whether there is a solution or not. Even if you knew how to do that, that actually solves a great number of mathematical unsolved problems that exists today. So it would have been keys to the kingdom if this was possible, but it's not. But then again, I think that's more interesting now that we know that it's impossible. It's interesting to ask, when can you say something about it? Anyways, I wanted to highlight one of the mathematicians. So she's not the one that did the last step of the Hilbert's 10th problem, but a good chunk of the the 10th problem. She's a female mathematician, Julia Robinson, born in 1919 and passed away in 1985. And she contributed a lot to computability theory and computational complexity theory, and a lot on the 10th problem. You might notice that we just had her 100th birthday last year. And in fact, at UW-Tacoma, we hosted Julia Robinson Math Festival last year. We were gonna host it this year as well. It was gonna be an annual event, although because of COVID-19, it got canceled this year. But I think we're trying to hold it still this year in the fall if things look better in the fall quarter. Anyway, she's an awesome mathematician, and female mathematicians don't get enough credit, so I wanted to make sure to highlight her here. Okay, I hope you found it interesting. If you find the subject fascinating, as I do, I would suggest picking up this book on Hilbert's 10th problem. It has a lot of interesting stuff. If you want to go through this, and there's like 3 or 4 good capstone projects in here. If you find this stuff interesting, talk to me and I can tell you more about it. Anyways, I think I want to end the video here. See you guys on Thursday.